We're talking about optical flow. I'm just going to extend over the basic equations and formulations that we derived in our last lecture. So remember, optical flow, really what we're doing here is to find point correspondences between images, okay? And we need that for epipolar geometry, we need that for structure from motion, we need that for shape from shading, you name it, right? For, the illumination cone, what have you, right? All these different algorithms that require point correspondences. So we've defined optical flow and motion field. You have them here. They are not exactly the same, right? The motion field is defined in 3 dimensions. So if there is this object, this oval object moving in this direction, that's not what we observe. We observe this other 2-dimensional motion. So with this basic caveat, we defined our most fundamental formulation for optical flow of point correspondences in our last lecture. And here's the model that we used, right? We said we start with an image I, and then the image I has, for pixels, say x, y at time t, I don't know why this is z, but anyways, should be equal to the image at x plus some u times delta t, where u is the motion about the x direction, comma, y plus v times delta t, right? Plus t times delta t, right? And v, it's the motion about the y direction, correct? This should be t. I don't know why this is z here. This constraint that we derived the other day is called the data conservation constraint, right? Which means that the data is preserved or conserved over time, that the only thing that occurs is that the information in pixel xi has moved to another pixel rp, right? That's it. So to do that, we derive the first order Taylor expansion of this criterion right here, which gave us this equation right here, right? So by doing the first order Taylor expansion, that allows us to linearize this model, right? And with that, we can equal this to 0 to find the maxima, minima of our criterion, right? And that gives us this criterion right here, which is the error function, E of the data, which is to integrate in some region of the image, this criterion that we have derived here, and I'm using the square function here for least squares, okay? I've defined. Now this this R region here defines the patch of the image where I am looking for the corresponding points, right? These are the derivations that we did on the board in our last lecture. So we have the function here. This is the first order Taylor expansion plus some other terms of higher order, which we consider to be 0, we eliminate. And then what we do is we consider that from image 1 to image 2, there's a very tiny, small differential of time that passes, and that gave us this derivation, right here, which we call the derivative of the image with respect to time, which is nothing else than the image with respect to x, right, and time, or x over time, the image with respect to y, and the image with respect to t, right? And remember that we called d of x over dt. This is our motion, or our vector that tells us the correspondence, right? The motion of the pixel, u about the x direction. V right here is the motion about the y direction, right? And ix, iy, it, we call them the partial derivative of the image with respect to x, y, and t respectively. And that's what gives us this data constraint that we had here before. Now, this is not sufficient, as we discussed, to compute a unique solution. So we need to add some other additional constraint. And we considered a spatial coherence constraint that we derive as follows. The derivative, or the gradient, of my motion field, right? The motion field is given by the motion vectors, uv, has to be smooth across the patch defined by r, okay? Meaning that if I have an object, like this one here, and this object is moving in this direction, then that pixel and that pixel are moving in similar, or are moving with similar velocities for u and v, right? That's all this means. Now, this is obviously true for all the pixels in that object, except for the points at the edge, right? Because that point here has neighbors, right? On top, there are correspond to the background or to another object behind it that are not moving or moving in another direction. Those are called point or motion discontinuities, rather, and those are going to give us a lot of trouble. Okay. Now, there is a way to solve this problem of motion discontinuities, which is to make this region R as small as possible, right? Because we don't want that region. So if we have, say, an object here is moving in this direction, and we have an object behind it that is moving in some other direction, right? We don't want our region, say, a region of this size, to include pixels from another object, right? So this would be perfect. Of course, if I locate that window right here, you will have a small number of pixels that correspond to the other object, right? And when I locate it right here, it has half of the pixels that correspond to another object, right? So the way that we can address the inconsistency in this constraint that we have here, the spatial coherence constraint, is by making that region very small, right? So that it takes longer for us to include pixels of other objects, right? For most of the pixels, it does not. But of course, remember that if we are to solve the previous equation that we had here, right? I want this region to be as large as possible to get as better a solution as I want. So that's going to give us problems. So we combine these two functions, ed arrow functions, right? ed and es, multiply es by some lambda, and then we solve this using gradient descent, as we have done before for nonlinear least squares, which means that we have to compute the partial derivatives of this arrow function, and that is the solution that we derived. The gradients are equal to this, right? And then we can iterate. I have posted in Canvas a chapter from a very old book by Horn called Robot Vision. It was published in '86. It has all the necessary mathematical background and equations to derive this basic formulation. Okay. All right. Now, remember that we don't live in the continuous space, but rather in the discrete space, or in the discrete image. And therefore, we need to estimate the derivatives of the image using pixels. And these are the equations that I derived the other day on the board that are given by this tensor that I've defined here, right? So this would correspond, for example, could be 4 pixels, 8 pixels, whatever you want to consider. This would be 4 pixels of the image at time k, and the ones behind would be the same 4 pixels at time k plus 1. And then with that, you can compute the partial derivative with respect to x by comparing the neighboring pixels, right, in the x direction. And you can do the same for the y direction, so there will be the x direction. You can do the same for the y direction, for the t direction, the time. All right. So let's see some examples of this. This is a very, of course, I'm selecting a problem for which this is not going to work, this basic formulation, right? So this is a very difficult problem. I have this block here, this square, white square, on black background, okay? And that the square is just moving 1 pixel by 1 pixel in that direction, from image to image. That's it, okay? Now, if I compute the optical flow, I set lambda equal to 1 when I ran this. If I compute the optical flow, now let's see what happens here. This is very interesting. Now, I have selected a window size maybe of this size, right? Small window size, because remember, that's what I want. I want a small window size so that ES, right, the smoothness constraint, is satisfied. It's not incorrect. And then what happens, let's look at the pixels here in this motion discontinuity. What happens is two things. At the pixels inside, or even in the boundary, right, this is only pointing downwards. Do you see the arrow pointing down? The reason is because if my window is of this size here, right, then all it sees, that window, is the motion of the block moving down. But it cannot see moving it toward the right because the pixels are of the same luminance, right? Now, if I had texture here, some shading, then I might be able to also detect the other. But if I don't, if the luminance is constant, then there's nothing I can do. The opposite happens in points that are in this other edge, right? The arrows point toward the right, 1 pixel to the right only. They don't point down because, again, that window does not see that block moving down. It only sees the block moving rightwards, right? This one's the same. But for points here at the corners, right, for example, this corner right here, then the window does see the neighbors and that point moving down and to the right. And now the arrow is correct, right? You see that? So how can we solve this? Well, there's two more problems, obviously. Inside here, right, if I have a region R inside this block, then that region sees nothing. Doesn't see the block moving down, right? Because all the pixels have the same luminance. It's oblivious to what's happening, right? And when I have my region located in a pixel outside of the block, the white block here, then that region does see some of this block moving, and it assumes that the background is moving as well, right? So we have all these different problems. All right. This problem of these arrows just pointing down, these arrows just pointing rightwards, and these pixels not pointing anywhere because you think are not moving, can be solved very easily by making the region R larger. If you make the region R large enough that it includes the whole object, then every pixel is going to see the object moving downward and rightwards, right? The problem with that, I don't know if I have, no, I don't. The problem with that would be that then more points of the background are also going to be considered to be moving in that direction incorrectly, right? Because you are adding more motion discontinuities. So something's got to give, right? Either you make the region small or large, and there is no solution with this basic formulation. Now, excuse me, this is called the aperture problem, okay? Now, one solution to this is to use robust statistics, which we have already introduced before, okay? So let's see how we can change our basic least squares formulation of the function f of x equals x squared, right, for something else, as we have mentioned before, in order to try to eliminate outliers. What would be the outliers? The outliers would be for a region small enough, because we want to keep the region as small as we can, to eliminate the points that do not correspond to the object moving, for example, right? Let's see how we can do that. That would allow us, if we could do that, would allow us to make the region larger, which allow us to solve the other problems. So we're going to go back to our basic definition of the data error function, ED. There was this function right here, remember, where rho of x was equal to x squared, right? That's a least square solution, okay? And this was the smoothness error function, which was the gradient square, right? But now I'm going to substitute this rho of x equal to x squared, right? That leads to the least square solution and hence the problems by some other function, as we have mentioned before here in class, like this one, right? Which looks something like this. This one right here looks something like this. And the reason we want to use this is because this approximates maybe this function. Now, let's go back to this. We've seen this before, but let's review. Rho of x equals x squared is equal to this function right here, right? So this is x, the x-axis is x, and this is rho of x, right, or x squared. Now, what happens is if x is small, this function works well, but when x is very large, like in an outlier, right, this function gives to that point tremendous importance, right, when it should not. So at some point we want to determine, okay, these are outliers, we want to cut them out, at least make them flat that they don't count more. This is nice, but this has a discontinuity in the derivative, and because we want to compute the derivative, we are going to compute the Laurentian function instead, okay, or Cauchy function. Okay. Now, if we use that, now we allow R to grow, right? You see that I have allowed R to grow, and all the vectors here are pointing in, are pointing in the right direction. You see they're pointing in the right direction, rightwards and downwards. And there is some minor point discontinuity around here, right? That even this method would not be able to solve, okay? But you agree that this is much better than what we had before, right? Okay, this is an example with a Coke moving toward the right. Real example, real data. These are very important. Another extension that we can do is to extend the modeling that we have provided here, right? So remember that I said in our last lecture that I assume that the pixel x, y corresponds to x plus u delta t, y plus v delta t, right? They're identical. But that's if and only if the illumination is constant and the object doesn't move in 3D such that the shading of properties of that pixel have changed. So even with a static point source at infinity, right, the shading of a pixel or the radiance that we observe in a pixel may change, right? So why don't we just add this into the model? It's not that silly to say, let's include these shading changes into the model. That's why we have derived all these things that we have. So for example, let's look at this. So imagine that we had this example that we had before here of this block moving 1 pixel to the right, 1 pixel down, okay? But now I multiply this by this illumination change, okay? By this shading change. Now I observe this, right? But all I've done is I've multiplied this by some illumination change, right? This would be probably a more realistic example with some texture inside that you can follow, okay? So in that case, what you have is that the image and its pixel, x, y, and t, plus the motion of that pixel, it's equal to the original pixel times that multiplier, right? This multiplier that I have here, plus maybe some error function or some additional term, okay, that I can add to occlude the object, to change the illumination, or turn off the illumination, turn on the illumination at some points, right? That cannot be described with a simple multiplier, right? So this is exactly the same model. If you take M out and C out, this is exactly the same model that we had before, right? But all I've done, I've added a multiplication term here and an addition term. That's it. Now, if we do the derivations of this, now we need additional terms. This is the same term that we had before. Nothing has changed, only that now since I compute the gradient of this function, this criterion, with respect to this other functions, right? I'm going to have what I had before, the partial derivative of the image with respect to x times u, plus the partial derivative of y with respect to of I with respect to y times v. And now I'm going to have, plus it, the partial derivative of the image with respect to time. And now I'm going to have minus the image times mt. Mt is a partial derivative of my multiplier term with respect to time. And ct, which is the partial derivative of the additive term with respect to time as well. Okay? Yes, question. Oh, there is a square missing here. You're correct. Yes, that should be squared. And that's over our region. And then now we're going to have 3 smoothing terms instead of 1, because I have the original smoothing term, right? That the gradient of the motion of neighboring pixels has to be smooth, right? This one here. But I'm also going to impose a smoothness on the multipliers and on the additions, right? They cannot change dramatically from pixel to pixel. So now I end up with this new error function here, E, which has ED, the original data constraint, ES, the original smoothness constraint, and this EM and EC that defines these other additional constraints. And I add lambdas to specify which of these constraints I want to emphasize. All right. There's also a way to solve this in closed form, and I have added this here. I'm not going to go over this, but there's a way to do this in closed form. So this is a synthetic example. This is random noise, right? That is moving according to this, is moving according to this function, meaning that this first half of the image, right? This half of the image here is moving in that direction. And this one, what is it? And the whole image is moving in that direction, right? And we have a multiplier of the illumination, which looks like a Gaussian, right? You see that? Sort of a Gaussian here. So if we use the basic formulation that we derived on the board in our last lecture, this is what we're going to get. Now let's see what we get. What we get is, we do get this U motion, right? I think U is in that direction, right? So we do get this U motion, right? You see it here. You do get this V motion as well, right? In here. But you have the effect of the illumination, right? That I had here, the Gaussian, having a huge effect here at that region, right? Because this model, I mean, it's not that the model is wrong. It's that the model does not include those possible changes. So of course it cannot deal with them, right? I would be surprised if it worked. So if I use the robust method I introduced today, where I change the least squares or the square function, right? The least square solution for one with a robust function like the Lorentzian, then I get this, which is much better. You can see that this part is almost perfect. This part is still really affected by the illumination, right? Huge effect. There's also an effect here at the center, but this is even more so, right? This area right here, which is completely incorrect. And this is not bad, right? It's still wrong, but it's getting better. And if you use this model, the new model that we have introduced, which does model the illumination, then this is the illumination that it estimates, which is pretty close to the real one, right? And this is the V motion and the U motion, which are, again, very close to the true one. So obviously, when you model things with the appropriate correct equations, then things work much better, right? Not surprisingly. You agree? That it's not surprising. That so what you need to get from this is that when algorithms do not work for you, it's because you're not modeling the reality of the physics of your world, right? And you need to change your definition of or you need to model it differently. So let's go back to this example I introduced a few minutes ago, where there's this white square that's moving in that direction, but I also multiply this by this illumination scalar, and I obtain this. And again, if I use the basic formulation, that's what you're going to get. Terrible, right? I mean, now, remember, here, we used to get these pixels pointing down. Now it thinks that it's moving in that direction because of the illumination mask. You see this illumination multiplier, that it increases in illumination in this way. So now this basic formulation that we derived last time is thinking that the object is moving in that direction. It's really, which makes sense, obviously, right? Because now the wider pixels here are moving wider toward that direction, right? So it makes sense. These ones have not changed, right? These are still pointing toward the correct direction. These are also wrong. But now the points that we had at the corners that were correct before are now incorrect, right? Again, because of the illumination. Now, if we were to use the original formulation, we're going back to the original problem that we had with the basic formulation, right? This new formulation can solve for this illumination change that we have introduced, but it cannot solve for the problem of requiring a larger region R to obtain the values of the interior of that white square and to get the correct direction for the pixels in every point of that object, right? That can only be solved by making that region larger, right? And that can be solved now easily, we know how, using the robust function, the Lorentzian function, right? So now if we de-derive this method, this new formulation, but instead of using the square function, the least square solution, we use the Lorentzian, the Cauchy function, then we're going to get the results that we were getting before with the robust method, right? All right. So again, this is just a few more examples. This is a classical way to compute or to test your algorithms. You just generate pixels here with random noise, right? You assign values from 0 to 255, select one randomly, and you create this textured square that the optical flow can now supposedly follow, right? And multiply this by the second image. You multiply it by a illumination change, difficult illumination change like that. See what happens. Basic formulation goes crazy, right? It's trying to find point correspondences, just can't. And why? Well, let's think about this. This texture here has completely changed, right? Because the basic formulation assumes that this intensity of that pixel here has not changed in here. So if you're looking, the algorithm is looking for a pixel here somewhere that is similar to this one in intensity, and it just doesn't exist anywhere. So it's just finding the closest match, possible match. But as you can see, everything breaks down, obviously. If you use the robust method, that wouldn't work either. And if you use the new method, it works much better. And I don't have the results here of this new formulation with the robust method, but that works really well. And that solves the problem. All right. If you want to work in DUS, or whenever you need to compute point correspondences, you need to evaluate in your application how well the algorithms that we have already discussed, right? I'll derive another algorithm today on the board, last one. But we have 4 algorithms already that you can use, right? The basic formulation that we talked about in our last lecture, the robustified extension of that formulation, which is by changing the least squares function for, say, the Lorentzian or Cauchy function, right, by a robust function. The extension of the new model, or the new model that we have defined today, that includes the illumination changes, for example, and occlusions and things like that. And the robustified version of that, right? So we already have 4. I'm going to define, as I said, a 5th and last one today. But whichever you want to use in your application, you're going to need to know how well is that algorithm actually working for me, right? And how are you going to measure this? Okay, there are 2 things that are important in optical flow. First thing is the magnitude of the optical flow. The magnitude means the length, right, or the norm of the vector. Okay, so is the vector of the ground truth the true point correspondence? So this pixel here corresponds to this pixel here, right? So this is my vector, the red one. The magnitude of that vector, meaning the norm of that vector, is the norm of VGT. Okay. Now this is the vector that my algorithm has estimated, and let's call this V estimate. Okay. Now the norm of this is the norm of V estimate. Now for all the pixels that I have in the image, I need to compute the distance, right, between that norm and that norm, right? So that would be the norm of this distance, or this difference of norms, right? So this is the norm of V estimate for the ith pixel, the norm of the ground truth for that pixel. I subtract these 2, and now I compute either the absolute value or the square or whatever I'm using, okay? And now note that if I have n pixels, I've changed these to n sub v. Now what n sub v means is that not all the pixels in my image have optical flow. Many pixels may actually either be occluded, may disappear, may correspond to new points that don't have point correspondences, right? May be uncomputable for some reason. So you always have to take into account that this metric only makes sense on the points that your optical flow gives you point correspondences for. Okay. Now, when you read this in the literature, you will see dense optical flow. And by dense, they mean that NV is either n, the total number of pixels, or very close to n. Okay? That you give an estimate even for points that become unoccluded or points that go occluded and so on. All right, so this is the first measure that you need to consider. This tells you how well you estimate the length of the motion, right? The distance of the movement of the pixel from image 1 to image 2, 2 to 3, and so on. But it's also important to measure how well you detect the orientation or the direction of movement. And that is given by that angle alpha, right? Now, if they were identical, then the cosine of alpha would be equal to 0, right? Because that would be exactly the same as this, right? And the larger that angle is, the larger the cosine is going to be, right? So I can compute the inner product. Now the inner product of these two vectors, or of, let's say, the inner product of two vectors of norm 1, of length 1, is equal to the cosine, right? You agree? So that is what I can use. So this would measure the cosine. Since these two vectors do not have norm 1, I have to divide by the norm of the two vectors, right? So this here is the cosine, and now I can compute the arc cosine if I want. And that's going to give me the angle, right? And that's going to be a measure of the angle, the angle difference between these two vectors. Okay. So I've given here an example. So I took this image and I crop it. First the red, then the blue, and the blue is 1 pixel, 1 pixel. So 1 pixel down, 1 pixel to the right. And then I also multiply by a Gaussian noise, Gaussian illumination change, excuse me, as before. And here are some results that you can look at for the angle, for the velocity error. So this would be the magnitude that we've talked about. This would be the angle. This is the density, means the number of points that we are using here in this equation. It means which percentage of the n pixels, the original n pixels, okay, that we are using, and so on, okay? All right. This is more examples. This is synthetic data generated from the Yosemite Valley. Sequence, more numbers for you to look at, some quantitative results that I've showed before. This is a robot that is moving toward the wall at the very end, and you can see this optical flow. This is actually very interesting. This is very useful for navigation, because when you move down a hallway, for example, right, or an alley, what happens is that the points, the pixels that correspond to points on the walls, the side walls, that are close to you, move really fast. And the farther away you look, right, the pixels that correspond to the wall, but they're farther away from you, move much slower, right? It's a decrease in velocity. And obviously, if you had an infinite tunnel, the points at infinity would have zero motion, right, to you. It will never move. So that's very typical. This is an example of this again. Tracking the motion of people, tracking the motion of cars, and this just for fun. There's no motion here. So after we finish point correspondences, this doesn't move, I swear. I mean, it's completely static. You have it in your slides online. You can print it out, and if you print it out, you'll be convinced that the print on paper doesn't move, right? And you'll still see this. The reason this happens is because of a frequency analysis that your visual system is computing at every instant in time. And we'll talk about this in our last part of the course that will probably start next week, when we start talking about functions and functional spaces. And we'll talk about Gabor filters, low pass filters, and all these things. And this is what actually yields this illusionary motion that you observe here. It has nothing to do with point correspondences. It's just an effect, very weird effect. And it depends where you look. If you look at different places in that image, then you see different parts of the image moving, right? But if you focus at one point, right? If you focus here, at this point here, it's not moving, right? But if you focus over here, then this starts to move, right? It's really odd. Okay. All right, any questions before we move on? All right, so let's get back to the board. All right, so let's see one more set of derivations for image matching. I'm going to call this more generally now image matching, okay? More general than what we have been calling it, because this, as I said, can be applied to epipolar geometry, right? In epipolar geometry, I need to find these point correspondences to solve for the essential matrix, the fundamental matrix, and all these triangulation problems that we had, right? The P and P prime, remember? It can be applied to structure from motion, right? Because for structure from motion, we have a sequence of images, and I need to know that point in the first image corresponds to that other point in the second image, and to that third point in the third image, and so on, right? That has to be given to me. And these algorithms, we're reviewing these algorithms because we need to have an algorithm that does this automatically for us. Because if we have to go to a sequence of, say, a few 100,000 frames, and I have to manually mark all the point correspondences, never going to finish, right? And in some videos, it could be millions of frames, right? OK. It also applies to tracking. So in some applications, you want to track an object moving, right? Self-driving cars, obviously, it's a classical example where you have another car that you're looking at, or a pedestrian or a bicyclist, and you want to track their motion, right? And that will allow you to predict where that car, person, bicycle is going to, right? And you can start making predictions of what's going to happen and what you need to do next. And so on. There are many other applications. So let's just start, as always, with some basic formulation for this image matching problem. And that will allow us to define a more modern method for estimating optical flow. Okay? I'm still going to call it optical flow, because the optical flow that determines the point correspondence, they're all the same thing. Right? All right, so let's just start with I, as before, our image. Okay, so this is be an image, say in RP by Q. Now, an image is not defined in the real domain, right? Because the pixels of an image just have a integer numbers, right? If you have an 8-bit pixel, excuse me, then it can go from 0 to 255, right? And so on. But it's usually convenient, mathematically convenient, to assume that they are real numbers. And that will allow us to use more general linear algebra and matrix computations. Okay? So we assume that they're real numbers. And let's say that the image is of P by Q pixels. Okay? So it can be defined as a matrix, basically, of P by Q. We'll let I of x be the pixel defined by, say, x equals to UV. Okay? So x is equal to the coordinates, the U and V row and columns, right? That define the location of the pixel in the image. And now we'll define a function, let's call it W, of x given some parameters theta, that defines the allowable image transformations. Okay, so this defines the allowable image transformation. With theta, let's say theta 1 through, I don't know, n, the parameters, okay? the parameters of this function. Okay, so far so good? Okay, so for example, let's define the W that we'll define the W that specifies the basic formulation of the optical flow that we derived in our last lecture. How about this? Okay. Okay, let's see if we can do that. Now, we want to have, right, here I of not x now, but wx given these parameters, right? And then we want to make this equal to the image before that transformation, right? That was our basic formulation. Yes? So if that is true, what should this transformation be equal to? Anyone? It should be equal to u, right? Or, well, I've called this u, yeah, u here, plus the first parameter, θ1, and v plus the second parameter, right? And now, if I sum over all the pixels in my image, I want this transformation to be as close as possible to, say, some target transformation, okay? And because I'm going to use least squares, I'm going to square that, right? So I want my image, according to that transformation, to be equal to the ground truth or the target, right? I'm going to call this the target. You will, more than target, you'll usually see this called a template. The template image. And that is because in image matching in general, not only in optical flow, but in all these other applications that I've been mentioning about image matching, right? You start with a template, right? A window, like, so let's go back to epipolar geometry, right? P was our first point, and we're looking for P prime in our second image. And we do a window around P in the first image, right? And that window is the template that we're now going to try to find in our second image, right? So that's why people call this a template. Okay? Make sense? Now, if you do object tracking, right? So let's say that you're tracking this object. You want to track this object, so you do a window around this object, right? And that's your template. And now when I move this and take another picture, you're looking for that template somewhere in the image, right, to see where it moved. So that's also template matching, right? All right, this is, in general, a nonlinear least squares problem. Which means that in order to solve it, we need an initial estimate for W, right? W of x, theta the parameters. And once I have this initial estimate, I can iterate using the nonlinear least square method that we derived earlier in the course, right? And we're going to have that W is going to be W of x and theta, the parameters, plus some increment of these parameters, right, at each iteration. Remember that? Okay. So this yields the least squares problem, or the following, should say, least squares problem. I sum over all the possible pixels that I have in my image of I, W, theta plus increment of theta minus the template image squared, because it's least squares. Now, to solve this nonlinear problem, right? Remember what we did? We compute the Taylor expansion, right? The first order Taylor expansion, for example. Eliminate terms that are of higher order, and then that linearizes the equation, and then we can solve it, right? By looking at the gradient. So let's do that. So the first order Taylor expansion is going to be the sum of x over all the pixels, I mean, of I, W, x, whoops. Oh, that was a mistake. Yeah, that's a parenthesis. All right, I've corrected this. Theta plus, no. I'm taking the Taylor expansion, so theta plus, what am I doing? Okay, sorry. This is still wrong, isn't it? This should be x. There you go. Now, I knew there was something wrong. X theta, right? There we go. Now that looks better. Plus the gradient of the image, the partial derivative of W with respect to my parameters, the increment of my parameters, and the target or template. And because I'm using least squares, I'm going to square this still. Yep. Okay. All right. Now here, as always, the gradient of the image is what we have derived before. It's the partial derivative of the image with respect to x and y, which we have called Ix and Iy, right? And W, the gradient of W with respect to its parameters is going to be equal to the partial derivative of WU with respect to the first parameter all the way to WU with respect to the last parameter, which is said to have n, and then the partial derivative of WV, right, with respect to the first parameter and with respect to the last parameter, okay? And anyone can remind me what this matrix is called? Very good. The Jacobian matrix. Excellent. Someone has been watching the lectures or doing the readings. It's good. Okay, so now we want to minimize this equation that we have linearized, this first order Taylor expansion. Now we can use linear least squares because it's already linear. So that yields, I'm going to take the derivative. So I have this 2 times over the sum of all the pixels of the gradient of I, the image, the partial derivative of W with respect to the parameters, transpose the image W x theta plus the gradient of the image times the partial derivative of theta increment theta minus tx. Okay? And I want this equal to 0. Right? I just took the partial derivative equally to 0 to find the minimum, as we always do in linear least squares. So this gives me the solution. I'm just going to solve for the increment that I'm looking for. It's equal to H inverse the sum over all the pixels x of the gradient of I times the partial derivative of W with respect to the parameters squared times Tx minus I W x theta and that multiplies here. Okay? Yeah? Is that correct? Where now H is equal to the sum of the gradient of I, the partial derivative of W with respect to the parameters, transpose the gradient of I, partial derivative of W with respect to the parameters, right? And again, anyone can remind me what this is called? The Hessian. Very good. That's a Hessian matrix. Good. So that leads us to our algorithm. Let's see our algorithm. Straightforward. It has 3 steps. That's it. Number 1, compute the increment of theta using this equation that I have right here. Okay. Number 2, modify the current parameters theta by adding the increment to it. And 3, repeat until this increment, the increment of theta, is smaller than some small value epsilon, right? That would determine. That's it. Right? That's nonlinear least squares, right? So this is a more general algorithm than the one we have defined before. 4-point correspondences for one main reason. And the main reason is because I have this function here that defines the allowable transformations. Okay? Now, let's go back to what we defined in our last lecture. We said that this W is equal to nothing else than an addition, right? So there is a motion about Y. So Y has moved from the U position to U plus something, right? And v has moved from v to v plus something. And that something could be negative, right? So it could move one direction or the other, right? Up and down, right or left. That's it. That was a basic optical flow formulation, right? But you could also, well, if you were to use robust statistics, that would be in the solution here, the least square solution. And still not change that. But that could also be changed to include multipliers, right? So I could add multipliers and illumination changes as additive noise and so on. But how about making or using some transformation that it's a little smarter than this? So this formulation works really well if I have a point right here, right? And I'm moving, so this is the camera right here, the image plane. And I'm moving this like this so that this plane remains parallel to the image plane, the physical retina, right? So if I move it like this, that works really well, right? What happens if I do this? Then I create in the image where I observe a shear, right? In the shape of this object. And what defines this? We've seen that. How can I model that transformation? As an affine transformation, very good, right? So now I can make W, for example, an affine transformation. My allowable transformation, it's an affine transformation, right? Why not? It's much better than just making I of x, y at time t, it's equal to I of x plus some u, comma, y plus mv, comma, t plus delta t, right? I mean, that's too basic. But if I allow now for affine transformations, that will look much better. So in general, we want W to define some appropriate, some useful, let's call it, transformation. Okay. Now, the only restriction on W is that it has to be differentiable. And the reason it has to be differentiable is because I need to be able to compute this, right? So I need to be able here to compute the partial derivative of my mapping function with respect to its parameters, right? So it has to be differentiable, but that's my only restriction, really, right? It can be anything else other than that. Of course, you don't want it to be an arbitrary function that would make absolutely no sense. You want it to define the physics of the world, right? Like the shear, the affine transformation we're talking about. So if we were to model an affine transformation now, remember that we have defined this before as a matrix A, right? A 2 by 3 matrix A and a 2 vector B, right? Correct? So for example, e.g., we could consider that we allow for transformations defined by a weak perspective camera model, right? And that, remember, is going to be given by W of x and the parameters theta is equal to, let's see, we had a matrix that had Ks01, where K and S define the aspect ratio, right? K defines the aspect ratio, that's the pixel, right? Whether it's a square or not. S defines the skewness of the physical retina, right? And it's just a 1. Now I have to multiply this by a scalar here in front which is for the weak perspective. What is it? What's that? Okay, very good. 1 over ZR. ZR is my reference point. This is the depth of my reference point, right? Very good. And now I need to consider both the rotation, right, and the translation of that object, right? So the rotation in weak perspective is given by what matrix? R2, which is, what's R2? Very good. It has 2 rows, right, that define the 2-dimensional rotation, because ZR is fixed and I'm not considering the 3rd dimension, right? And very good. And then I have also the translation vector, right? And now this is my transformation, and I need to multiply this by U and V, right? My pixel that I have there. Okay? So far, so good. Now, let's complicate things a little bit, just a tiny bit, okay? It's just going to allow to do very interesting math. I'm going to consider a composition of these functions, these allowable transformations. I'm going to create a composition of them. And I know it looks weird, but bear with me for a second, okay? So I'm going to do a composition of these functions. And by composition, I mean that we will apply or use, we will use our function multiple times. So for example, I could do the image of, instead of x before, so I had x theta, and before I did no, what am I doing? I had image of x, and then I did the image of wx given the parameters, right? That's what we've done before, right? That's the allowable transformation. But I could do the image of w x. Now, instead of the parameters here, I'm going to consider the increment of the parameters, right? Do you still have that in here somewhere? Okay, maybe, oh, there it is. This part, right? I'm going to consider this part right here, right? So note that this is a transformation of x given these parameters plus the increment, right? But I could just do first the increment, right? And now, okay, hold on. And now what I'm going to do, okay, I'm going to do the function again, right? So now consider that this, I have done already the increment, and now the original theta, right? So what is this equal to? This is equal to this. I haven't done anything weird, just that then this, right? And within this, in a composition, I have added these other parameters, right? So it's just another way to describe this. This composition is the same. I could write this in a composition. This is very typical. This is the same as w x theta is given by wx theta composed with wx increment. Okay? And this operation is typically or sometimes called the compositional algorithm. Okay, so if we have this right here, right? Now the least squares problem for this new formulation is given by the sum over all the pixels x of I w w x given the increment of the parameters, given the parameters, minus our template window, right? Our template image. And I'm using least square, so this is squared, right? Yep. You see that? Okay. Now, not surprisingly, right? I'm not going to redo all the calculations, but not surprisingly, you see that this is the same as this equation. So if you do the derivations again that we have done, you're going to end up with the exact same solution, right? I mean, duh. You're not expecting to get a different solution, are you? Right? Okay. So this is going to give us the exact same solution. So now you're asking, okay, so if this is going to lead me to the exact same solution as before, same solution I had before, right? Then why did we do that? We did this because now we're going to change. We're going to play around by noting that I can move that transformations, right? Not, or I can apply rather these transformations not only to the image I, but also to the template T. So if I do this, this is what I'm going to get. I could define, for example, the sum over all the pixels. Now let me start with the template. I could take the template and listen. This is what I'm going to do. I'm going to apply to the template one of the two transformations. Let's say the increment of theta, right, to this, okay, minus my image wx the parameters, okay, and I'm going to square this because it's still least squares, right? Okay, see how this works? This is sometimes called the inverse compositional algorithm. And I have uploaded in Canvas a paper that has a beautiful description of these two algorithms, the compositional and the inverse compositional algorithm, okay? Okay, you can write it like this, in which case you're going to have that your transformation over x given the parameters theta is the same as the composition of wx given the parameters and wx given the increment of the parameters inverse. Okay, that's why this is called like this. Now, let's derive the solution because this solution may be different. So let's derive the solution for this inverse compositional algorithm, okay, as we did before. How are we doing on time? Oh, we are out of time, are we? Okay. All right. This longer than a minute that I think or 2 minutes I may have left. So let's leave it at this. We'll derive the least square solution for this problem. Again, what you need to do, you were asking for practice of problems, right? Derive this at home, and we're going to derive the solution here in class on Thursday, so you can practice these things, right? Take the first order Taylor expansion, linearize this, solve for linear least squares, right? Derivative equal to 0, find the solution as we've done here on the board today, and that'll yield you the inverse compositional algorithm. All right? Okay, I'll see you Thursday.